Dear colleagues, good afternoon. First of all, I would like to thank organizers, and it's a great pleasure for me to have this opportunity to speak today about our project. This is a joint project with Wojciech Patkas and Krzysztof Pachucki. Project was being carried out for last few years. The goal of the project is to improve theoretical accuracies of energy levels in helium and bring this accuracy on the level of precision achieved in modern experiments, and also to allow determination of the nuclear charge radius of helium to be compared with nuclear charge radius extracted from Munich helium, as we have heard from Randolph Paul today. I would like to start with a short introduction, in which I would like to point out that there are just two different methods today for systematically describing QED effects in atomic structure. These two methods are different by the way they construct the perturbation theory. We have two parameters in the theory relevant in this context. One of them is the parameter Z alpha. This is the electron nucleus coupling strength parameter, and it regulates relativistic effects in our system. The second parameter is 1 over Z, and this is approximately the ratio of electron-electron interaction to the electron-nucleus interaction. So this parameter classifies the electron-electron interaction. So for heavy systems, it is advantage to start to use QED in the Fari picture. This picture, the interaction between electron and nucleus is included into the zeroth order approximation. So we include all orders in Z alpha, but we use perturbation expansion in the electron interaction in 1 over Z. And of course, there is expansion in alpha, which is a standard expansion parameter in QED. So we expand in 1 over Z and in alpha. For light system, on the other hand, it is advantages to start with non-relativistic Schrödinger equation, in which we include the Coulomb interaction between all particles. So we include all orders in 1 over Z, but we expand in relativistic effects in Z alpha, and of course in alpha. Today we are interested in helium, so this is the way we will build our theory, but we will also keep in mind the alternative method which will be used for cross-checking, and in the end of my talk we will recall about this. So for light system, the underlying theory is non-relativistic QED, and here we usually do not distinguish between alpha and Z alpha. We assume that there is just a single expansion parameter, alpha. The general statement is that each terms of this expansion are represented as expectation value of some effective Hamiltonians, some effective operators on the non-relativistic wave function. Generally, this expansion is quite complicated. It includes some logarithms of alpha, and some of effective operators are non-local. The starting point of this expansion is non-relativistic energy, which is of order m alpha square. Then there is leading relativistic correction of order m alpha 4, leading QED correction, and then higher order QED corrections. So we will now briefly walk through all of these corrections. So the basis of all is non-relativistic energy and non-relativistic wave function, which are obtained by solution of Schrödinger equation, which contains the Coulomb interaction between all three particles. Today we can solve this equation very, very efficiently. The wave function is represented as a combination of angular and radial parts, and it is well acknowledged today that to achieve high accuracy, the radial part should include dependence on all three radial variables R1, R2, and R12. So this is what is called explicitly correlated wave function. The radial part is usually represented as a linear combination of some basis function and nonlinear parameters, which are usually implicit in these basis functions, are obtained from variational principle. In our calculation, we use the basis function consisting of exponentials. This basis was introduced for helium calculations by Vladimir Yerokhin. And it's a very powerful method, and one of important advantages is that all radial integrals with such wave functions, basis functions, are calculated analytically and very efficiently. So there is just a single master integral, which is just a rational function, and all others integrals are obtained by differentiation or integration of this simple formula with respect to nonlinear parameters. It is important that all radial integrals, not only for non-relativistic energy, but for relativistic corrections and QED corrections, are calculated analytically with this basis. This is very important for our calculations. And today we can solve Schrödinger equation with this or also other basis sets essentially to arbitrary accuracy. So for example, here you see the table for the ground state energy of helium, and it is now known up to 45 digits. Of course, for practical purpose, it's kind of overkill, but we usually try to keep the non-relativistic energy accurate to about 20 digits, which gives us about 10 digits of accuracy for matrix elements. So now we have good relativistic wave function. We can proceed further. The next step is the leading relativistic correction. And it is given by expectation value of the bright Hamiltonian, which is known for a very long time. And so suppose we are able to do angular momentum algebra for matrix elements, we get immediately the relativistic correction essentially to also arbitrary accuracy. Please note that I do not write here the recoil correction corrections here or in later formula. Of course, they accounted for, but I do not wish to present this formula to simplify things a little bit. The next step is the leading PD correction, and it is of order m alpha to the 5. The formulas are also known for a very long time, and in them we have several new features. One of them is this operator 1 over r cube. The matrix elements of such operators diverge on singlet states. So what stands here is a regularized operator defined by this formula. It looks a little bit complicated, but in fact one can derive closed form expression already for a regularized operator, and its calculation does not present any difficulties. On the other hand, this quantity here is called Bessel logarithm, and it is the first case of a non-local operator. So it is represented by a sum over the whole spectrum of Schrödinger equation. And this sum is pretty tricky because it's very nearly divergent. So there are significant contribution from very highly excited continuous states. And it was for quite some time a difficult problem to calculate, but by now we know how to do this very well. There are different approaches. The approach we use goes back to papers of Schwarz and more recent work of Vladimir Yerokhin, and in it we use the integral representation for the Bessel logarithm. So the integral goes over the momenta of the virtual photon in the self-energy loop, from which we subtract the ultraviolet asymptotics. So essentially this is the method of calculation. We can calculate the integrand very accurately. We subtract numerically the ultraviolet asymptotics and perform the integral, and the tail of this integral, high end of this integral, is usually performed by fitting the integrand to the known asymptotic expansion form. And so this calculation can be controlled to very high accuracy, and at present it is also well established. And now we are leaving the part which is well established and cross-checked by different calculations to the part which is much less known. So in order m alpha 6, the corrections are of two types. There is an effective operator to this order, and there is also the second order iteration of the relativistic correction. The problem for a long time was to derive these expressions, and moreover to eliminate all divergences which appear in singular operators. It was solved only relatively recently by Christoph in 2006 for helium, and later on we extended those calculations to helium-like ions. And finally, the corrections of order m alpha to the 7, and this is the subject of our calculations for the last few years. And the structure is similar. So there is an effective operator to this order. There is a second order iteration of low order operators, but there is also a low energy contribution which represent as a relativistic correction to the Bessel logarithm. I will not go into details, but I would like to speak very briefly about some problems which are experienced in those calculations. One of the problem is constellations of divergences. So divergences are of the two kinds. One sits here, and the operators are singular, and the matrix element diverge. And the second kind of divergence sits here, and it arises only through summation of Schrödinger spectra. So matrix elements are finite, but this sum of the spectrum diverge. And the first step is to transform all divergences to first order matrix element, and this is achieved in transformation of the operator to such form where this is a regular operator which does not create any divergences, and this is anti-commutator of some other operator with non-relativistic Hamiltonian. Inserting this, we arrive with second order correction, which is finite and doesn't contain any divergences, and more complicated first order operators. Divergences in these operators are regularized by using dimensional regularization in coordinate space. They are localized at cusp points where two coordinates are equal. They are identified and algebraically cancelled using the cusp generalized cusp conditions. Wojciech Patkas did a great work on this. It was very long and difficult algebraic calculation. The second kind of the problem is more numerical, and it concerns the calculation of relativistic correction to the Bessel logarithm. So this is again the standard Bessel logarithm of order m alpha 5, and we need relativistic correction to this, and it arises as a correction to the Hamiltonian here, to reference state energy, to wave function, then to current, and finally this is the retardation correction to the current. For example, to give you an idea, so if we take this retardation correction, we will have this corrected integrand of this form, which contains an addition k square as to the non-perturbation. So we need to integrate it over all possible photon momenta after we subtract the ultraviolet asymptotics. But instead of just two terms for the standard Bessel logarithm, here we have to subtract how many 6 terms of large k asymptotics. So the idea of the calculation is quite similar to the standard Bessel log, but numerically it's much more challenging. Now I'm coming to our results. So this results for triplet S-state in helium, and we have a list of individual contributions as we see the expansion in alpha indeed converge quite well for helium case. And here we have our previous estimate for M-alpha-7 contribution, as was done in 2010 on basis of hydrogen results. And this is our present calculation. So we are in previously estimated error bars. And the whole uncertainty comes presently from estimate of effects of order M-alpha to the 8th. So we see that this calculation improved theoretical accuracy by a factor of 25. And you also see that we are sensitive to the nuclear size effect on the level of 2%. Here we use the nuclear radius as obtained from Munich helium experiment, as we heard today. And this looks good so far, but when we compare with experiment, we see that there is quite some problem. The first line here concerns the 2p to s transition, and it agrees with experiment perfectly. But if we switch to transition between different ends, we see already significant deviation, and moreover, in comparison with very recent experimental results for ionization energy of individual state, we see again systematic deviation. So it looks very much as both triplet S and triplet P energies are off from experiment by 0.4 megahertz. And this is a problem we were working on since 2001 for a year. And the working hypothesis is that there is something wrong with our calculation of M-alpha-7 effects. And my remaining time, I would like to tell you what we did to check for this. We did several quite important tests, and one of them is matching coefficients of log alpha and log z. To explain what it is about, let us come backwards to the leading QED contribution of order M-alpha-5. So these are very well-known formulas, and how they are presented. Usually, there is an electron nucleus term which contains log z alpha, and electron term with log alpha. However, it is a little bit less known that there is also log z, which is sitting in this matrix element of a singular operator. And the coefficient at this log z is exactly the same as the coefficient at log alpha. So we can join them and write these known formulas in different way, where there is only logarithm of z alpha and parts which do not contain any logarithms. So this matching of logarithm is quite surprising. We don't know, because we don't know why it is so, but it is in all formulas we can check so far, we know today. And we checked that this also true for contribution of M-alpha-7. So this is formula for the logarithmic contribution to M-alpha-7, and there are quite many operators here. This Q operators is some basic operators which we don't know, we don't need now their forms. But the point is that they are joined together to build logarithm Z alpha. So essentially, all electron terms here were derived twice. Once as a coefficient at log alpha, and second time as coefficient at log Z. These both parts match together without any remaining contribution. So this very effectively cross-check checks all electron logarithmic contributions. Now the second test we did is what we call hydrogenic limit. So the point is that if we know the Z dependence of our results, and if we come to very large Z, then the electron interaction dies out. That means we have the approximation of non-interacting electrons, which we know from hydrogen theory. Technically, to get this limit, we need to perform our calculations for different Z, which we did, and then fit our results to the form of 1 over the expansion, and these coefficients C0 will be known from the hydrogenic limit. So if we do this for individual terms, we see some significant disagreement, but when we collect all parts together, we see a very convincing agreement with hydrogen theory. So this is our calculated M alpha 7 correction as a function of Z. So we cross-check this leading coefficient of 1 over the expansion against hydrogen theory. And even more, we can cross-check the next coefficient of 1 over the expansion against all other calculations which are performed by different methods. And here there is also consistency, but it is not, the accuracy is not very good, so it's not so conclusive. So I'm coming to summarizing our present situation. So we performed calculations of complete effects of order M alpha 7 for triplet states of helium, which was published last year. Now we performed such calculation for helium-like ions, and we have preliminary results. These calculations allowed us to analyze the Z dependence of this correction, and we made some important cross-checks. So for helium, these calculations improved theoretical accuracy by about a factor of 25. We are sensitive to the nuclear size effect on the level of 2%. But our results are different from experiment by about 400 kilohertz, and we still don't know why. And in this context, it's of course very interesting to see what will come out from helium-like ions, and we heard in the previous talk that they have very good progress on this, so we are very much looking to the results. So thank you for your attention.
Thank you, Vladimir. Any questions?
I have two questions. First is concerning non-relativistic theory. in the wave function expansion, you have a double summation L1 and L2. Is it right? How far do you, how high do you have to go in L1 and 2? Because theoretically, just for the P states, just one term would be enough. So
you mean this
in non-relativistic wave function,
yes.
we use, I understand, the forgiven total angular momentum, you have a double summation L1 and L2 for all electrons. Am I right?
The point
just use a minimal form.
Not really. This for P state there is just one contribution
So
here.
you use one. Okay.
Yes, for D state there will be two parts.
Okay, okay. Yes. So you don't. I have another question. I see that if you do non-relativistic quantum dynamics, electrodynamics expansion, there is a substantial drop of the size of the correction if you go from even order of alpha to odd order of alpha. But if you go from odd order to even, it's only 10% reduction. Is it some fundamental reason for that? Just the accident for the correction you calculated?
Well, there is no really fundamental reason, but the magnitude of this term actually comes from hydrogen theory. Yes, and a large contribution of M alpha 7, it's actually due to one loop self-energy. So it will be alpha, Z alpha to the 6 for hydrogenic self-energy, and it is large because there is low energy contribution. This relativistic correction to the Bessel logarithm, it is large. So because of this.
We have a question from the online attender. Thanks for the great talk. Could you say a few words about numerical integration in beta logarithm and the alpha 7 correction? Vladimir, try to answer quickly.
Yes. In fact, there is not much numerical integration here. This interval is separated in two parts. Low energy part and high energy part. For low energy part, the most safest way is to perform full diagonalization of the matrix and do this integration analytically. And for high energy part, what we do is to fit the K dependence of the integrand to the known form of the asymptotic expansion. So we know this first coefficients analytically. The rest we don't know analytically, but we know the form. So there will be the form will be the same as here. So there will be log K, there will be square root and powers of 1 over K. So we fit this and then we integrate analytically. And of course, we change everything to make sure that we keep the accuracy under control, and that's essentially the most tricky part.
Thank you, Vladimir. Next question, please.
Thank you for your nice talk. I have a question about the wave functions. Is there like any possible single triplet mixing included?
Yes. The singlet triplet is included into order alpha 6. Yes, here we built a perturbation theory for isolated level. So all singlet triplet is included as a perturbation correction as order by order. In more difficult cases, when we have hyperfine mixing, then one need to build really a matrix and consider perturbation theory for quasi-degenerate states. This is not the case here.
So you showed that the triplet S to triplet P transition, actually you calculate right, and you agree with the experiment. And that implies that if you think there is a problem, both the triplet S and the triplet P are affected in the same way. And I wonder whether that doesn't give a clue of what could be wrong, because actually S is completely different from P. And you look, it seems like you agree on the D. And to me, this is very puzzling. So I don't know whether you can comment on this or whether my remark is absurd.
Well, that certainly is puzzling, but the triplet singlet mixing is relevant only for P states, because there is a small difference between singlet and triplet P levels. For S states, the singlet triplet mixing is practically not important numerically.
Yeah, Gordon Drake here. I might have missed something, but where did the M alpha to the 8 terms come from? Was that, I thought that you'd have to derive new operators for that.
But for one loop results, we know results to all orders. So we essentially can take the higher order residual for that. And for two loop, we take what we have for hydrogen, and we know it at least as good as for hydrogen.
No, this is radiative, two loop radiative and one loop radiative. And so Vladimir includes one loop radiative and two loop radiative.
Yes,
these are the dominant contribution, because the Dirac contribution means the pure relativistic is negligible in comparison to the radiative corrections. Is non-radiative part is very small. Next questions? Are there any questions? Okay, please.
So I was wondering if the vertex correction was included in the alpha to 5 corrections that you calculated?
Yes, vertex correction is actually present in Bessel logarithm.
Okay. Do you plan to extend these method to the hydrogen?
No, theory of hydrogen is much more advanced than for helium. Everything which we do for helium is already known for hydrogen.
Maybe the question was about H2 molecule, hydrogen molecule, not the hydrogen atom. You have to be a bit more precise when you ask questions. So do you really mean hydrogen molecule? Okay, so the question about the hydrogen molecule. Vladimir,
well, this is more a question to Krzysztof, because there are different people for different systems.
Yeah, so once we resolve this problem, we go to the hydrogen molecule. We have to resolve this problem, because we cannot, because of discrepancy. Once we resolve this discrepancy, there will be next talk also about this discrepancy, because they really indicate that we really have a discrepancy. Just wait a few seconds, we have the next speaker. So but maybe there are further questions. Yes, there are.
Hi, I just wanted to ask about the basis functions that are being used, and I guess admittedly I don't know exactly where they come from, but I wondered if you could speak to are they reliable for the full range of R1, R2, and R12, or is there a sort of special limit where you stop trusting that basis set?
Well, I'm not, probably we have not yet reached this limit where you don't trust the wave function.
Yes. These are the most reliable basis set you can imagine, because it satisfies the cusp condition at small r and asymptotic contribution large r. This is the best, the exponential basis is the, especially correlated exponential basis is the best basis for many electromagnetic systems. The only problem is the difficult to do the integrals. or more than 2 electron systems. Any further questions? Yes.
Yes. Hi, Vladimir here. I have to ask this question, I guess, just to make sure that I got your last page correctly. So despite the discrepancy you see in these transitions with higher N, you're about to publish the transitions for the triplet states up to carbon, right? Or do you want to find?
Yes, yes.
I have to correct, not to up to carbon, much more.
Okay.
Yes, up to 12 actually.